Recording already. So let's start. So other two videos we already did in Collaborate Ultra. So that's there. So this is the last video for the chapter 1, and we start the chapter 2. Yeah, good. So what I'm saying here is the molecules are not flat, they are not flat, so they don't look like this paper, so they look like this book. You see that they have length, they have breadth, they have height. So you see that, so the molecules look like the three-dimensional object. They don't look like a simple paper. They are not two-dimensional. So for example, let me write one molecule here. That is methane. All right. So this is a methane molecule. So it looks like this. And if I draw this in the board, it looks like C H and H. You see that it looks like a plane. So it looks like this paper, right? It looks like a plane, right? But in actual, this molecule is not like that. This look like this. You see? This carbon look stays here, and this hydrogen goes away from this board. It just penetrates and goes away from this board. You see that? So if there is a hole here, and you put a stick like this, and that at the end of that stick, that is connected. You see that? So this, you see, this hydrogen here goes away from the board. Is not in the board. This carbon is on the board. This carbon is on the board, but this is going away from the board. Yeah. So this one, the down here also going away from the board. You see, this is also going away from the board. See, these two are going away from the board. Make sense? And there are other two here. This one here, this hydrogen is coming toward me. So this is going away. This is coming toward me here. It's turning toward you. And another hydrogen here is also coming toward me. You see that? So the molecule actually look like this. You see? So carbon is in this board here. Hydrogen and this hydrogen are projecting toward me, and this hydrogen and this hydrogen are going away from the board. So molecule look like this. That is called three-dimensional structure. So in reality, all molecules, atom, whatever we study in chemistry, look like that. Yeah. So that's, they have length, breadth, height, radius, diameter, everything we can measure. Make sense? That's great. So that's the methane. So if you see something like this, this is the happiest molecule in the world. They have no strain. So something at the center, and the four things are just connected like this, and this is the very happiest molecule, and we will talk later what that means. So this is called tetrahedral molecule, and we have some bond angle here, and we will measure those, and we'll talk about those things. Yeah. So the molecules are really not flat, not two-dimensional. They are three-dimensional. They have length, they have breadth, they have height, they have radius, they have everything. So if you have to really draw this molecule, this one and this one are coming toward me, this one and this one are going away from me, and this is in the board. Make sense? Good. So the molecules are like that. All right. So now let's talk two things here. I talk about extensive and intensive property here. So there are many properties, and these two properties are extensive and intensive property. Extensive, EXTENSIV, extensive and intensive property. Intensive property. All right. So very important. In future, if you go to the higher level, you will be seeing this kind of stuff in your course, like engineering or nursing or different type of course in higher level. You will need to know this extensive intensive property. It's a thermodynamics term, and everybody teaches this concept. Yeah. So extensive properties of any material depend on mass, MASS mass. It depends on mass. All right. But intensive property don't depend on mass. Don't depend on mass. Very important. Don't depend on mass. So what does that mean? Extensive property depend on mass, intensive property don't depend on mass. So what does that mean? So you see, let's say you have 1 kg ice here. You have 2 kg ice here.
Doing anything out of this?
This is 1 kg ice, that is 2 kg ice. You see, now measure the volume. Which has more volume? 1 kg ice has more volume or 2 kg ice has more volume? Of course, 2 kg has, right? So 1 kg is like this much, and 2 kg is like that much, right? And if it is 20 kg, it's like even bigger, right? So the volume is bigger than the mass. Make sense? Great. So you see that 1 kg ice has large volume. Sorry, small volume, and 2 kg ice has large volume. And if you take the 100 kg ice, it even has a big volume, very large volume. You see, so the volume is the property we are looking here. So the volume depends on mass. If you take small amount of mass, it has small amount of volume. If you take bigger amount of mass, it has bigger volume. If you take a very big amount of mass, then you have a very big one. Make sense? Yeah. So this depends on the mass. You see that? So extensive property depends on the mass. So the volume is extensive property. Extensive property. Why? Property. Why? It depends on the mass. Smaller the mass, smaller the volume, bigger the mass, bigger the volume. Right? And similarly, there are the mass itself is extensive property. If 1 kg is this much, 2 kg is this much, right? So mass itself is extensive property, and the volume is also extensive property. Let's talk about energy. Now I talk about energy here. So energy. How about the energy? You see, energy. Is it extensive or intensive? Now I need to find out. Now you probably already know in high school how to calculate the energy. If you are calculate the energy, potential energy, you have mass, acceleration due to gravity, and the height, right? So this is the potential energy. You see, there is a mass term. So if you have a bigger mass, when you put those numbers, it gives a bigger value. If you have a smaller mass, put those value and calculate, it gives a small value. So energy is also extensive property because it's exclusive. It depends on mass. You see that? How about the kinetic energy? What is the definition of kinetic energy? Half mass velocity square. You see? Now again, if you have a bigger mass, you have a bigger kinetic energy. If you have a smaller mass, you have a smaller kinetic energy, right? Depends on the mass. Make sense? Great. So all energy are extensive property. Energy. All volumes are extensive energy because they depend on mass. Alright. Now let's talk about the intensive energy. So I finished the extensive energy there. So when you go home, you just look those PowerPoint slide I post there, and you'll have a better idea, and you can email me if you don't understand. Yeah. Good. Now let's talk about intensive energy. You see, intensive property. So do not depend on mass. So let's say the temperature. Let's say if the temperature depend on mass or don't depend on mass. Say this is a snow or ice, right? This is snow or ice, and divide this into many pieces. And in one bucket, put this much ice, and in another bucket, put this much ice. You see, a lot of ice. Maybe here is a 1 gram ice. Maybe here is a 1,000 gram of ice. You took the ice and put in a small amount here, and in another bigger, you put a lot of ice there, right? Now put 2 thermometers here. Put 1 thermometer here and measure the temperature. So maybe it's reading about 0 degree. So it's reading 0 degree centigrade. Now put another thermometer here and read the temperature. It also reads the 0 degree centigrade somewhere here. You see that? This is a small amount, 1 gram mass. It gives the 0 degree. You take another big amount of mass, now it also gives the 0 degree. So the temperature didn't depend on mass. Either you take a small amount of ice or you take big amount of ice, you measure the temperature, and the temperature was still the same, right? So does temperature depend on mass? No, it doesn't depend on mass, right? So it's independent of the mass. That's the intensive property. Make sense? Good. So temperature is independent to the mass. And if you look the book, or anything, there is no way you will see the temperature is equal to mass multiplied by something. You see that? So in any equation, that doesn't come in the uh, temperature is equal to mass something. Yeah? Good. So now let's see another one. The temperature intensive property. I have another example here. Let's say if I have anything. Um, let's say density. You see, now again, let's take water, small amount of water here. Let's say you put 5 milliliter water here, and in another bucket, let's say you take 1,000 milliliter water, right? You see, or you can say this is our mass. Let's say you put 5 grams, in another you take, let's say 1,000 grams water, right? Now let's measure the density. Put your density measuring device here. It will show 1 gram per ml. And put another in it here, put density measuring device here, it will show 1 gram per ml. No matter where you measure the water density, whether you go to lake or you measure the density of water in a beaker, a small amount, a big amount, or you go to the ocean and measure the density of the ocean water, no matter where you go, the density of water is always same. Make sense? You see? So the density, you take the 5 gram of water and measure the density, it shows 1 gram per ml. A lot of mass here, and you put the density measuring device there, and it's also showing the 1 gram per milliliter. So it is also intensive property. It doesn't depend on the mass, right? You see, I measure the density here in small amount. I got the same result. I measure the density in the big amount, and I still get the same. So density is also intensive property. You see, so it's a very easy way to check whether it is an intensive property or extensive property. You see, if you see something like this, you see, uh, gram per ml. How many units are here? 1, 2, right? You see, gram is a mass, ml is a volume. 2 units are in density. This is the unit of density, and this is gram in ml. You see, there are 2 units together. One is up, another is down. So that is intensive. You see, if you see specific energy, you see joule up there and gram up down there. You see how many units are there? There are 2 units. So if you see something like in a measurement or in anything, if you see 2 units, one is up there and another is down here, something like this, they are all intensive property. Yeah. The ratio of 2 extensive property is the intensive property. Make sense? So you see, so the density is gram per ml. So it's intensive. Specific energy also joule per gram. Intensive. But if there was only energy that is just mgs, something like this. You see, it's a extensive. It depends on mass. You see that? So if you calculate this, this will only give joule. There are no two unit here. See, so if you see energy that is extensive, depend on mass. If you see specific energy, 2 unit here, 1 joule up there, the gram here, there are 2 units, so that is intensive. So that's the difference between how you can check easily whether it is intensive or it's extensive. Make sense? Good. So if I give you, is energy is intensive, extensive property? Yes, it is extensive property. It depends on mass. But how about specific energy, which has 2 units here, maybe 2 joule per gram. So this is intensive. Yes. Good. So let's see. So you'll see a lot of those things in future. All right. So there are a couple of questions I write, so you can go home and do those there. Now let's say what I have here. Now let's talk about the physical properties of things. Properties. Physical properties of things. Physical properties of things. So, what is the height of someone? What is the how long are the length of the arms? What is the color of the eyes? So those properties are the physical property, right? So physical properties are simply how they appear. How they appear. So you don't have to break them into chemically into different composition. You just go there and take it and measure it. That's called the physical property, right? So physical property are basically appearance of things. Appearance, how they appear. How they appear, all right? And so how something, why something appears like it appears. Let's say water. Water is, this is water. Water is, the molecular formula of water is H2O. Water is liquid. Why water looks to be liquid, right? Now another, let's say hydrogen sulfide. Hydrogen sulfide. This is gas. You see, why water look liquid and why hydrogen sulfide looks to be gas? Why? This is a physical property. The physical property is a physical property. How does it look like? Liquid. How does it look like? Yeah. So why they look like that? So they look like that because of their molecular attraction, molecular attractive properties. All right. So let's say why water look like the liquid? Here is the thing. You see, water molecule look like this. Water molecule look like this. Now I water molecule here. Another water molecule look like this. You see, there are two water molecule I am writing there, right? Now the oxygen has negative charge, hydrogen has positive charge, this hydrogen has positive charge, oxygen has negative charge, hydrogen has positive charge, and this hydrogen has positive charge. So distinctly water has, one end has a positive charge, another end has negative charge. You see, now one molecule, oh sorry, I wrote the other way. I should have written this other way, sorry. Like this. You see, oxygen has negative charge, hydrogen has positive charge. So I am just writing two molecules. You see, now this part has positive, this has negative. So what do the positive and negative charge do each other? They attract, right? Positive attract negative, negative attract positive. So you see, now there is a force developed. This is negative here, oxygen, there is positive here. So their force, a kind of force is developed. They attract each other due to that one. So that is called hydrogen bond, hydrogen bonding. See that? This force is called hydrogen bonding. So this force, because this force bring all molecules together, so they become liquid. Make sense? If there was no force like this molecule fly away, and this molecule fly away, and they are all in gas phase. Make sense? Good. So see that the water is in liquid form because the molecule are like that. Hydrogen has positive charge, oxygen has negative charge, negative and positive attract each other with great force, so they tend to stick together, and they are in the liquid phase. Make sense? Very good. I will be asking this kind of question in exam. Why water is liquid and why hydrogen sulfide or something else is gas? Yeah. So let's see. Let's look the hydrogen sulfide gas here. Now I put the hydrogen sulfide here. Hydrogen sulfide. So this is hydrogen sulfide here. Hydrogen, sulfur, hydrogen here. And let's say I write here another sulfur, hydrogen, hydrogen. You see that? Hydrogen sulfide. Sorry. Hydrogen sulfide. Maybe sulfur there, maybe hydrogen here. You see? Something like this. S2S, right? S2S. Hydrogen sulfide, 2 hydrogen. Exactly like S2O, S2S. You see? So there was in water, I told you there was here was a negative, here was positive, here was a positive, here was a negative, here was positive, so they would attract here. But in this case, in case of the hydrogen sulfide, they don't have negative and positive. So they don't have negative and positive. So this molecule cannot attract this molecule. You see that? So what happens if something cannot attract? Can they stay together? They can't, right? So stick together, you must attract each other so that you can stick together, right? So there is no force of attraction between these two molecules, so they fly away from each other. So that S2S is in gas phase. Make sense? Good. This is very important concept in chemistry. It's called the hydrogen bonding. So if I say, if I think I already posted in homework why water is liquid and why S2S is gas, right? So because H2O, there are in oxygen there is negative charge, hydrogen positive charge, so they get the molecule of one in attract the other, so they stay together. So they are that's called hydrogen bonding. So the boiling point is very high. and they are in the liquid phase. But in case of S2S, sulfur doesn't have negative charge, hydrogen doesn't have positive charge. So there is a reason why they don't have a positive or negative charge. So we'll see something. Yeah? Good. So there is no positive, there is no positive charge, there is no negative charge, there is no positive. So the molecule can't interact each other. So no possibility of formation of hydrogen bonding there. Yes. Good. So you see, there are different. General chemistry covers so many things. So many things. We cannot master all concepts because there are too much things. So we just focus certain things so that we must understand those things. You see. So we will do that. Now. So the physical property is the function of intermolecular forces. If the intermolecular forces is high, they tend to be solid. If intermolecular force is a little lower, they tend to be in the liquid. But if intermolecular force is very low, they don't attract each other, they tend to be the gas. That's the idea. See that? So if here is one molecule, here is another molecule or atom. So they attract each other very tightly. They tend to be in the solid state, like this computer, table, whatever we have. But if this molecule and this molecule attract with a little less force, so these are mobile. This moves, there is a force and they tend to be in the liquid phase. But if this is a molecule, this is a molecule, they don't attract each other. You see, they don't attract it. There is no interaction. So goes this way, this goes this way. See, now they are in the gas phase. Make sense? So the physical property are the function of intermolecular forces. Intermolecular forces high tend to be solid. Intermolecular forces very low tend to be gas. If intermolecular forces is between solid and gas, they tend to be in the liquid phase. Make sense? Good. So let's see. Why boiling point of water is 100 degrees centigrade and boiling point of methane is minus 161 degrees centigrade? Methane gas already in the gas phase. They boil it minus 160. You see, so it's the same thing. So water has a hydrogen bond. So if you want to boil them, you have to cut that hydrogen, right? So if you want to boil the water, you see, what you should do is, so there is a force between this. This is minus, this is plus, this is plus, this is minus, this is plus, this is plus. So this plus and this minus are attracting each other, making this kind of force called hydrogen bond. If you want to boil the water, you need to cut this. How do you cut that bond? By giving the heat. If you give more heat, molecules start to just move around, move with more velocity, and they just go away from each other. So we need to cut this bond by giving heat so that the molecule gets separated and the water becomes gas. The boiling point is very high, right? Good. So, but in case of methane, for example, methane is like this: CH4, CH4. This is one molecule. This is another molecule. This is another molecule. You see that there is no plus, there is no minus here. There is no plus here. There is no force of attraction between these two molecules. So they already methane gas is in the gas form. You see? So this is in gas form. Let's see something. So that's it. So what are the physical properties? The physical properties are color. If you see color of something, that is physical property. If you are looking whether it is a liquid, gas, or solid, this is also physical property. All right. So how they appear and the melting point and boiling point, melting point of something and boiling point of something. For example, water has boiling point of 100 degrees centigrade. The ice melting point is 0 degrees centigrade. So this kind of the properties are called the physical properties. And the density, so these kind of properties are called physical properties. So whatever, without going to the laboratory, whatever you can see, you can feel, they all are the physical property. But to know the chemical property, you need to mix two chemicals together and you have to look what is produced. So whatever you are seeing, this kind of thing, they are physical property. Now, let's see what I have here. Now, here is the concept. It says physical property change with temperature. Physical property change with temperature. Physical property change with temperature. Change with temperature. Simply, let's say water. You have water. Let's say it's a 25 degrees centigrade. The room temperature water is 25. Put in the deep freeze, it becomes solid, right? It becomes ice, right? So this is water. Water at room temperature is 25 degrees centigrade, and it is in the liquid form. We drink it. Put in the deep freeze. Put this water into deep freeze. Deep freeze, you will see ice. So that is maybe 0 degrees centigrade. You see the physical state change. This was liquid. Now ice is solid. When the temperature change, the physical state change, right? Now boil it. Boil this liquid water. You will see vapor, water vapor. You see now this is a gas phase. So physical property change with temperature. If the temperature is really low, they try to be in solid. If temperature is somewhere a little bit higher than low temperature, they try to be in the liquid phase. And if the temperature is really high, all the liquid becomes like the gas. You see, so that if the temperature is increased, things try to be evaporate and becomes gas. Yeah? And if you cool something really cool, everything becomes solid. Yeah? Good. So the physical properties kind of the temperature. So if you change the temperature, the volume change. If you change the temperature, the density change. If you change the temperature, the state, like liquid, solid, or gas, they change. Make sense? So all physical properties change with the temperature. Yeah, you can do this physical property change thing in your home just by looking water, putting that in deep freeze, or boiling it. This all change by temperature. Yeah, good. So now how about the chemical property? Let's see. Chemical properties. So okay, we have time. So chemical properties. Chemical. So what are chemical properties of things? You need to put two chemicals together and you see how they behave. That is called chemical property. See that? So take a chemical A, take another chemical, put them together and see what material are formed. That is called chemical property. Right? So let's see. I want to look the chemical properties of hydrogen. Chemical properties of hydrogen. Hydrogen. You see? Now I have this hydrogen here. I want to mix with oxygen. I mix with oxygen here and I burn it. I burn it. You see, I have a test tube here. I have a hydrogen here and some oxygen here. And now I want to burn it. Burn. Now I will see water. You see how the hydrogen behave in presence of oxygen. Hydrogen behave in presence of oxygen by giving fire a little bit. It gives a liquid water. You see, so this is called a chemical property. So how in presence of other is called the chemical property. How one chemical behave in presence of other is called chemical property of that thing. Make sense? So how about the hydrogen chemical property of hydrogen with in presence of chlorine? You see, now I have a hydrogen in the test tube, I have a chlorine in the test tube. So they react and they give hydrochloric acid. You see, this is also the hydrogen the chemical property of hydrogen. It gives the acid. This is different thing. This is different thing. And these two different things react and they give the another new thing. It's completely different from hydrogen, completely different from chlorine, hydrochloric. You see, hydrogen burns, hydrochloric acid doesn't burn. Chlorine gas extinguish the fire. You see, hydrochloric acid also it's again this is a liquid form. This is gas. This is gas. This is completely new material, new properties are being formed. You see, now these things in the left side we call reactant. In the right side we call product. You see that? So this and this react together and then they give this thing in that. So the left side is called reactant, what is mixed together, and from that mixing, whatever is formed, that is called the product. Make sense? Good. So whatever I'm teaching here, this is already in the PowerPoint slide. When you go home, you can just review those. Yeah. Good. Now How about the models? So a scientific model here is a thing called scientific model. Scientific SCI, I don't know, scientific model. Actually, we cannot see what does the atom look like. When I go to the, I have some water in a beaker. I can know how does the water look like, right? How does the water molecule look like, or how does the hydrogen atom look like? So to know those things, with the scientists, the researcher build a lot of models to explain those things, and they are called scientific models. So in next class, I will be bringing here how does the water molecule look like, how does the methane molecule look like. So they are the models, yeah. So to visualize the atom, to see, because I don't know how does the atom of this table look like. So those to visualize the structure of the atom and the molecule, people develop the some uh, solid thing, so that we can visualize, okay, water molecule looks like this and methane molecule looks like this. So they are called the scientific model, yes. So scientific model, not only even if you go to the higher level and something people cannot explain, they just give some mathematical model. They just whatever the math says, they say, okay, my mathematical model shows this. I don't know if it is right or wrong. You see that? So if you see the mathematical model, okay, what we need, which day the COVID will be maximum in Wisconsin. So they all come from mathematical model. You see? So they are all the scientific model. Uh, that's a scientific model. So what is the atom? This we will be repeating this atom and molecule all along this course. So I don't define what is molecule and what is atom here. So if you have a only one thing, let's say the only one thing here, let's say in H2O, you got, there are two atoms of hydrogen and one atom of oxygen here. So this is a molecule, you see. So if there are more than uh, two or two or more than two atoms sticking together, that is called a molecule. How many things sticking together here? Two hydrogen and one oxygen, right? So these three things are sticking together chemically. So this is a molecule. So if I cut into three parts, one hydrogen, another oxygen. You see, so these are three atoms of two things. So there are two atoms of hydrogen and one atom of oxygen. We'll talk a lot about the atom and molecule, how do they look like in future. Yeah, in another course. So basically, if you have, let's say you have a gold here, you start to cut into many pieces. Keep cutting, and finally you reach to the a tiny particle. You can't cut after that. So that smallest particle is called atom. Make sense? So take a thing, start to cut it. Keep cutting, continuously keep cutting, and finally you will get a tiniest particle, and after that you can cut it. That tiniest particle is called the atom. And that atom has all the property of whatever you are cutting. You are cutting the gold, right? So whatever this gold has, the property has the same property that tiniest part of that gold has. Atom has the same property of that big chunk of element. Make sense? Good. And how about the molecule? Same thing. So now for the molecule, you need to take something like, let's say you have the water here. This is water, and keep cutting that water. Keep cutting that water. Keep cut, and finally you will reach to the tiniest part of that one, and out of that one, take the tiniest part, and that is the molecule. You see, and this one molecule has the same property of this all water. So this water molecule, one final water molecule, has same property of this bulk water. Make sense? So whatever this compound has, the characteristic have, that tiniest molecule has the same property. So that's how we define molecule and atom. But in future we will be talking more on these things. Yeah. Now there are some examples. Now I will do those examples, and maybe before going to the example, you can actually look those example yourself. So change. So let's say now there is a couple of concepts here. So the basic principle of energy. Basic principle of energy. So basic principle of energy is there are two kind of energy. One is kinetic energy, another is potential energy. potential energy. So if something is at rest, and if I calculate the energy of that rest of potential energy, yeah. So let's say I have the object here. This is my ground here, and I have a ball here, just staying there. I know the height here, and I know the acceleration due to gravity of this place, and now it is staying there. Now, how I, and the mass of this object is m. So the potential energy is mgh. You see, that's how we calculate. That's a potential. If something is at rest, and that has some energy, and that is called the potential energy. So you all have potential energy now because you are sitting and you are not moving. You see that? So that's the potential energy. If anything is at rest, and that the energy associated with that object is called the potential. And that's how we calculate. So you are given the mass of that object, and acceleration due to gravity at the place is 9.8 meters per second square, and you measure the height from here to here, and you plug those numbers here, and whatever comes, that is the potential energy of that rest object. Yeah. Alrighty, so how about the kinetic energy? Anything is moving, something is moving, and you want to know the energy of that thing, and that is called the kinetic energy. Yeah, so that is the rest, is the energy of the rest object, and kinetic energy is the energy of the moving object. So let's say this here is a ball, and this is moving this way. You see, this is moving. Now we want to calculate how much kinetic energy this moving ball has. Simple. The kinetic energy formula is half mv, half multiplied by mass multiplied by the square of the velocity. So you need to know what is the velocity of this object, what is the mass of this object. When you put the mass there and velocity, and you square and multiply it, and you get a number, and that much kinetic energy is with that substance. Make sense? So if something is moving, the energy associated with it is called kinetic energy. Actually, there is nothing in rest. Everything in the universe is moving. Alright, so things only comes to rest at minus 273 degree centigrade. If you see things, so we all, even though you are sitting, the molecule inside you are moving. If there is a water, it's not moving, the molecules are moving. You see, even if this computer, I don't see it's moving, the thing inside, the electrons are moving. So everything in the universe is moving. You see, everything is moving. So if you want to say, let's say you have a water here and water here. So probably you don't see they are moving, but it's moving, it's water. But if you want to make it don't move, you have to cool it to minus 273 degrees centigrade, and only everything comes to rest. And nobody in the world or the universe have been able to come to minus 273 degrees centigrade. So there is no temperature that is people cool things to minus 273. They can go to minus 272, 272.9, but they can't reach to minus 273 so far. You see that? All the molecules in things are continuously moving. So we need to calculate what is the molecular kinetic energy, those kind of things. Yeah. So this is the lowest temperature people are trying to reach. They can't reach here. Yes. Good. So at minus 273, all motion stops. All right. So there are the potential energy. For example, we eat food and we get the energy, right? So all the food contains the energy. That's potential energy. So electrons are moving in the conductor, bringing us the electricity. They are also kinetic energy because the electrons are moving. And just you read those kind of thing here in the PowerPoint slide, and it's good. So now let's see a couple of things here. The accuracy and precision. So there are something when we do laboratory experiment, there are a couple of terms we need to know. So precision, precision, precision. So what is precision? Let's say I tell you measure the mass of this guy here. So this is a thing, you need to measure the mass, right? Now you go to lab and one time you measure the mass to be 2.3 gram. Another time, second time you repeated the experiment, you measure the mass of this guy and you got 2.31 gram. And another time you measure the mass and you got 2.09 gram. You see? So something like this. So you have this thing and you go to the lab and you measure the mass of this 3 times. You see, you repeated the same thing 3 times. Are these numbers close to each other? Yes, you see 2.3, 2.31, 2.09, very close to each other, very good precision. So we want to be like this. You see that? So this is very good precision, good precision. We are doing the same thing with this thing, and I measured 3 times, and I got this very close to the result, very close to each other, right? So we are very good. We are doing very good scientists, right? So you need to get something like this. This is good precision, but you go to the lab and you measure the mass of that guy, and one time you got 2.0, another time you got 3.1, 1 gram, another time maybe 5 gram. I don't know how you did it, right? So you see that are these close to each other? No, one is 2, another is 3, another is 5, right? They are not close to each other. So this is not good. So this is, the data are not close to each other. So this is bad. We didn't do good. Maybe you didn't know how to use the balance, or the balance is broken, something like that. There are a lot of ways to make the error. You see that? So this is not good. So this is bad, not precise. I don't want you to remember the definition, long definition. I don't give those kind of thing in exams. So I don't say defined precision. I don't put those kind of question. I say, did you understand what precision means? So you just give, okay, I have a ball and I go to the balance and I measure 3 times and I got this number and it looks like very close to the result precise. So I want something like that. Yeah. So don't try to memorize the long definition of the book. Just understand this thing, yeah. So how about this is not precise? Good. Now let's talk about the accuracy. Now I give what time I have? Still 10 minutes more. So let's see. Now let's say I only know the mass of this guy. The mass of this one is 2.5 gram. You don't know. This is, I know it. Or whoever the company make this kind of thing, the company knows it. Yeah. So let's say you have a bottle here that has a chemical. Let's say it's a hydrocortisone. So it's a hydrocortisone cream. So there is 0%. So they know this because they have big company and they have the very experienced people to work. So they really know how much hydrocortisone inside is here. You see that 0.5% is the purity of hydrocortisone here. Now, rest 95.5 is all kind of the filler. That's not the medicine. Maybe there is water, maybe there is something else, maybe there is other powders. You see, only 0.5 out of 100 is the medicine. You see that? So these levels are the true value. This is a true value. All right. So let's say I have this mass and I know the company knows the mass of this guy. Now our job is to bring this in our lab and measure the mass of this one, right? So let's say we measure the mass of that one. One time we measure 2.3 gram, another time 2.4 gram, another time maybe 2.52 gram. You see, these numbers are very close to each other, right? Very precise, very precise. And these numbers are very close to the true value here. You see that? True value. This is a true value. The company knows it, or your instructor knows it, right? True value. See, so this experiment is very precise, and these numbers are close to the true value, right? And then accurate, precise and accurate. So you see, we want to be like this, precise and accurate. We want to know the how much mass here. These are the mass I got, and my number are very close to each other. So in doing experiment, probably we can't be accurate, but we can be. We should be trying to be precise. So measure one time, get one number. When you do the second measurement, you should try to get the similar number as the first. The third time also try to measure and then get the. So we try to be precise. Yeah. So if you cannot be precise in the laboratory or in the experiment, you are lost. So we try to measure the. I'm okay. I can fix later this value. Whether this value is true, my values are true or not. I can fix that later. But my measurement, I should be trying to get the values close to each other. That is called You see, I am precise because my three values are close to each other, and my values are very close to the true value, so I am accurate here also. You see, now how about here? I measure the mass of that one, and I got 3 gram, 2 gram, 2.4 gram, maybe 0 gram, maybe 2.49 gram. You see, in this case, my values are close to each other. I am precise, but my values, I'm just sorry, that's maybe 3.2 gram, maybe 3.5 gram, maybe 3.8 gram. You see, my values are close to each other, so I am precise, but my values are not close to true value, so I am not accurate. So I am precise, not accurate. Make sense? Good. This is very precise. I am precise, but not accurate. So in the laboratory, we are looking to be precise than being accurate. You see that? Now, good. So and read it later, and I post the homework, and you when you go home just do the homework, the similar concept there. Yeah, good. Now one more thing, no matter where you go in the universe, how expert people you meet in your life, nobody can be accurate, nobody can give you an accurate answer. You see that? Always, we always make error. So I work in 20 years in the chemistry laboratory, and if you tell me, can you read the burette for me? Can you read the volume for me? I can't exactly read the volume. So I always make mistake. You see that? So nobody in the world, in the universe, are perfect. So they make error. So we need to do error analysis. So let's say the error analysis. Error. How to do error analysis? Error analysis. So you see, I told you this, the mass of this guy accurate value is 2.5 gram. Who knows this? Only the company who make this knows that this is the true value. Now our job is to measure the mass in our lab, right? So that's the true value. Only company knows. Only we got the company that made that knows that value. Now I bring to my lab at UWEC, and I measure the mass. And it comes to be 2.2 gram. You see, 2.2 gram. You see that? Now, this number and this number are not same number, right? You see, 2.2, this is 2.5, right? Now I need to make some, either my measurement are good or not good. You see, now what I do is, I have two things to do here. One is absolute error. So absolute error is just take the bigger value and subtract the smaller value. If it comes big here, you take from you subtract from this to this one. But if it is big here, subtract from this to this one, and that is the absolute error. So 2.5 gram minus 2.2 gram is equals to 0.3 gram. So that is my error. Make sense? That's my error. So whatever the company give you the number, that's the true value. Whatever you measure in your lab and you got that one, that is your experimental value. So that is the absolute error. Now one thing. So now I check with the relative error and we go home. Relative error. This is important. Relative error. So whatever the error you got here, absolute error here, you see 0.3 gram. Take that value there and divide by the true value here. You see true value here 0.2.5 gram and multiply by the 100. You see, so what is this number comes? Let's say if my calculator works here, and okay, 46. So we still have a couple of minutes and will be good. Let's see, that is 0.3 divided by 2.5. So that is 0.012 multiplied by 100. So that is 100. You see, I made just 1.2% error. This is percent here, 1.2% error. So I'm very good. So if your error comes to be 10% or below 10%, you did very good job. So if it is more than 10%, we need to repeat the experiment again. Yeah. So anybody who makes a 10% error, 12% error, or around those errors, it's okay. It's acceptable. Nobody can make like the 1% error, 2% error. You see, so below 10% are acceptable value. Yeah. So something like this. So somebody may report like 10% plus minus 2. Maybe that error is 12% or 8%. So any error that comes around 10% or below 10% are good, and you did a very good job. Yeah. Make sense? How did I do? Very good. Thank you very much. Yes. Already. Let's stop this one.